In this video, we'll be looking at section 6.3, which covers inverse trig functions. Now, we've talked about inverse functions before, just not in terms of sine and cosine. We said that a graph represents a function if it passes the vertical line test. We said that a function is one-to-one if it passes the horizontal line test. And if a function is one-to-one, then it has an inverse. The problem is sine and cosine are not one-to-one because the sine and cosine graphs both oscillate, so they don't pass the horizontal line test. They hit the graph more than once. So if we want to define an inverse for sine and cosine, what we're going to do is we are going to take just a piece of each of the graphs that contains 0. So if we think about the sine graph, we can restrict it to negative pi over 2 to positive pi over 2 because in that domain, we hit all of the y values that sine ever hits, but we don't ever repeat a y value, so we pass the horizontal line test of this. For cosine, we restrict our interval to 0 to pi because, again, we hit all of the y values cosine ever hits, but we still pass the horizontal line test. We haven't looked at the graph of tangent before, but it's just a bunch of these swooshes upward, and at pi over 2 and every pi multiple of that, there are these vertical asymptotes. So this doesn't pass the horizontal line test either because obviously we're going to hit more than one of these. So for tangent, if we want the inverse, we're going to restrict the domain to this swoosh attached right to the origin. So we're going to restrict that to negative pi over 2 to positive pi over 2. Notice that with tangent, when we're restricting it, we're using parentheses on negative pi over 2 to pi over 2, and that's because of the vertical asymptotes. We can't actually include them. Whereas with sine and cosine, when we restricted their domains, we were allowed to include their endpoints. So let's try to break this down as much as we can. For angles in the interval negative pi over 2 to positive pi over 2 inclusive, if the sine of theta equals a, then the inverse sine of a equals theta. So what that does is it undoes what we did before. So what was our input is now our output. What was our output is now our input. And you can see here that this is our restricted domain. For angles in the interval 0 to pi, if cosine of theta equals a, then inverse cosine of a equals theta. And for angles in the interval negative pi over 2 to positive pi over 2, if tangent of theta equals a, then inverse tangent of a equals theta. And like we mentioned before, inverse sine, we're restricting our, we haven't talked about this. Inverse sine has the domain of negative 1 to positive 1 and the range negative pi over 2 to positive pi over 2. The reason being, this negative pi over 2 to positive pi over 2 is the domain of sine that we're restricting it to, so it becomes the range of inverse sine. The range of sine, how we restricted it, was negative 1 to positive 1, and that becomes our domain for inverse sine. The same follows for the other two. So you might remember those swishes that tangent was. If we take inverse tangent, because our range in tangent was all real numbers, inverse tangent has a domain of all real numbers, and then we restricted the domain of tangent to negative pi over 2 to positive pi over 2, so that becomes the range of inverse tangent. So we're going to see if we can work with some of these inverses. First up, we want the inverse sine of 1/2. So what that's asking is, what angle has a sine of 1/2? So I'm going to go to my unit circle. How handy is that? And I want to find an angle whose sine is 1/2. Since this is the unit circle, the y value of a point is the sine value. And it looks like that happens here at 30 degrees, which is pi over 6 radians, as well as over here 150 degrees, which is 5 pi over 6 radians. But remember, for inverse sine, we restricted our domain to the first and fourth quadrants. We said negative pi over 2 to positive pi over 2. So our answer is going to be this 30 degrees, which is pi over 6 radians. Yeah. Next up, we want the inverse sine of negative square root of 2 over 2. So I need to find a y value in quadrant 1 or quadrant 4 of negative square root of 2 over 2. It's not focusing. I'm sorry you can't see it, but it's happening at my angle 7 pi over 4, which is 315 degrees. But when we restricted our domain for sine, we said it had to be between negative pi over 2 and positive pi over 2. Okay. Come on, let's focus better. There we go. So we said that sine has to be between negative pi over 2 and positive pi over 2, and this is happening at 7 pi over 4. We have to find another way to write that so that it is between negative pi over 2 and positive pi over 2. Well, it has a reference angle of pi over 4. We're just going in the opposite direction. So this is negative pi over 4, and in degrees, that would be negative 45 degrees, which is negative pi over 4 radians. We need the inverse cosine of negative square root of 3 over 2. For cosine, we restricted it to quadrants 1 and 2, so I need to find a place there that has a cosine of negative square root of 3 over 2. In my unit circle, cosine is given by the x value, so that appears to happen here, which is 150 degrees, or 5 pi over 6. And then we want the inverse tangent of 1. Tangent doesn't actually appear on our unit circle, so we have to remember that the tangent of theta is equal to sine of theta over cosine of theta. But we know that the tangent is supposed to be equal to 1. So if 1 is equal to the sine of theta over the cosine of theta, then that means the sine is equal to the cosine. So I need the x and y values to be the same. So tangent, we restricted to negative pi over 2 to positive pi over 2, and I need the x and y values to be the same. That happens right here at 45 degrees, which is pi over 4. These inverses take a little while to get used to remembering the right quadrants. So make sure you're getting some practice in and remembering where we can actually use these, so where our answers can come from. We're going to work with some inverses in a way that hopefully will make some connections between the sines and cosines and triangles. So first up, we want to solve for these indicated angles. So I want to find angle A. I know the adjacent and the hypotenuse. Which of our trig functions deals with adjacent and hypotenuse? That's cosine. So I know that the cosine of my angle A is equal to the adjacent 6750 over 8100. I want to solve for angle A, so I need to undo this cosine. So I'm going to take the inverse cosine of both sides. That undoes the left, and I get A is equal to the inverse cosine of 6750 over 8100. This is something I can type in my calculator. Notice that it wants A in degrees, so I need to make sure I am in degree mode. And I want the inverse cosine, which is second cosine of 6750 divided by 8100. Looks like that is 33.56 degrees. Next up, we have this triangle here. We're trying to solve for angle X. We have the opposite in the hypotenuse, so that would be sine. The sine of angle X is equal to the opposite 2.5 over the hypotenuse of 5. So if I take the inverse sine of both sides, I'm going to get X is equal to the inverse sine of 2.5 over 5. And the inverse sine of 2.5 over 5 is equal to 30. In this case, X is equal to 30 degrees. Finally, we're looking at this triangle here, trying to find angle X. I know the opposite and the adjacent, so that sounds like tangent. So the tangent of angle X is equal to 300 over 400, meaning angle X will be the inverse tangent of 300 over 400. The inverse tangent of 300 over 400 equal to about 36.87 degrees. So that's one way we can use inverses. We're going to continue working with inverses, but we're actually going to work with some composite functions here. So first up, we want the inverse cosine of the sine of pi over 6. When we're dealing with composite functions, we start on the inside and work our way out. So I'm going to start with the inside, the sine of pi over 6. Pi over 6 is in radians because we don't see a degree symbol, and that's on my unit circle. Pi over 6 is right here. I want the sine of it, which will be the y value, and that's 1/2. So now that I know the sine of pi over 6 is 1/2, I'm trying to find the inverse cosine of 1/2. So I need to know what angle has a cosine of 1/2. Cosine is the x value, and it looks like that happens up here at pi over 3. Remember our inverse cosine? We can only pick from quadrants 1 and 2, and that's why I'm not picking this one down here. Inverse cosine only has us looking at quadrant 1 and 2. Now these next two are a little bit different because the inverse function is on the inside, and that makes things a little bit funky. But I think a picture really helps with these. So first we want to find the sine of the inverse cosine of 4/5. So we need to find what angle has a cosine of 4/5. I'm going to draw a triangle, and if I let this be my angle, I know that the cosine of that is 4/5. So the adjacent is 4 and the hypotenuse is 5. So this angle satisfies the fact that the cosine is 4/5. I just need to find the sine of that angle. I need the opposite side. Using the Pythagorean theorem, I want a different color marker. If I call this x, then x squared plus 4 squared equals 5 squared. X squared plus 16 equals 25. Subtracting 16 over, x squared equals 9, and x is equal to 3. If I know that's equal to 3, then I can find the sine of my angle. It's opposite over hypotenuse, which will be 3 over 5. The next one is very similar. We want to find the sine of the inverse tangent of 7/4. So I'm going to make a triangle so that my angle has a tangent of 7/4. So if I let this be my angle, tangent is opposite over adjacent. So if my opposite is 7 and my adjacent is 4, I'm trying to find the sine of my angle. So I'm going to need the hypotenuse. I'm going to use the Pythagorean theorem again. 4 squared plus 7 squared is equal to, I'll just call it C because it's the hypotenuse. That'll be 16 plus 49 is equal to C squared. So that's going to be 65 is equal to C squared. If I square root both sides, I get C is equal to the square root of 65. I'd really get plus or minus the square root of 65, but since it's a length, we're going to go with the positive. So this is the square root of 65. So the sine of my angle is the opposite 7 over the hypotenuse square root of 65. Ew, gross, I have a square root in the denominator. So I'm going to multiply by the square root of 65 in the numerator and denominator. And we get 7 square root of 65 over 65. We're going to run one more, very similar to this. It's just going to look a lot harder, but it's going to be the same idea. We're going to find a simplified expression for the sine of the inverse tangent of 4x, for x being restricted between -1/4 and +1/4. Don't worry about this part. It's just making sure that we stay in our domain. We want to simplify this guy. So just like the last time, I'm going to make it so whatever angle I'm working with has a tangent of 4x. That marker's not happy. There we go. So if this is my triangle, I'm going to let this be my angle. The opposite over the adjacent is 4x. So if I let my opposite be 4x, then I can make my adjacent be 1. So I've satisfied this inner part. I want to find the sine of my angle. That means I need the hypotenuse. I'm going to use the Pythagorean theorem yet again. We get 1 squared plus 4x in parentheses squared is equal to C squared. That's 1 plus 16x squared is equal to C squared. So my hypotenuse is going to be the square root of 1 plus 16x squared. You cannot take the square root of those separate. It doesn't work that way. You can only take the square root as if everything is squared. So that's my hypotenuse. So this is the square root of 1 plus 16x squared. I want the sine of my angle, and that's equal to the opposite, 4x, over the hypotenuse, the square root of 1 plus 16x squared. Ew, there's a square root in the denominator. You know what? I don't care this time. It's such a complicated expression. We're just going to leave it.